Hello everyone. Today in this video I'll be trying to see how to get the equation of a plane, Cartesian equation of a plane from just three Cartesian points. Okay, so let's get started. At first let us define what the points are. Like you are given the points, of course. These points have x, y and z, so we are going to show them, right? The x, y and z's are, let's say this is point r1, this is point r2, this is point r3. So R1 point has the coordinates x1, x1, y1, z1, and R2 has the coordinate x2, y2, z2. R3 has the coordinate x3, y3, z3. Okay, so if we are going to show the vectors going from R1 to R2, this is R21, let us define it that way, and this as R31. Bad R31. Oh, so what can we really do? We can get the vectors out of this, right? How can we? We can consider these points and say these are the vectors, okay? And these are the components of that vector, stated in a list manner, right? So if we try to see what R21 is, this vector, of course, these two are vectors, and R21 will be equal to R2 minus R1. This we should already know by now. So of course, so if we subtract R1 from R2, then we will find that the coordinates are also subtracted in the same manner. So the coordinates will be x2 minus x1, y2 minus y1, z2 minus z1. So in the same way, we will find R31 to be x3 minus x1, y3 minus y1, z3 minus z1. Okay, we found the two vectors. Now what we will do is consider a fourth point, and we'll name it R4, and they will have x, y and z as coordinates. Also, the vector from R1 to R4 will be named R41, right? So y, x, y and z, these are variables. R4 is equal to x, y and z. These are complete variables, okay? These are not constant like x3, x1, y1, y3. These are constants, but x, y, z are variable, because we are going to use this R4 as a generic point or an arbitrary point of this plane. Okay, so that's the point, an arbitrary point on the plane. Okay, so what are we really trying to do here, establish here? We are trying to prove that this will be a plane, arbitrary point on the plane. I think you can say that we are going to fit a condition here. We'll see in a minute. What we right now need is R41, right? So R41, which is also a vector, R41 is equal to x minus x1, y minus y1, z minus z1. Okay, so usually if three vectors, let's say u1, u2 and u3 are not in a plane, let's say they are not in a plane, then what they will do is, let's say the u1 u2 plane, of course two vectors make a plane, right? So I mean define a plane if this point is specified, of course. Okay, so this is a parallelogram, but as we have added another vector, what will happen is this will be a 3D construction, a three-dimensional construction, which is kind of like parallelogram, but it is not exactly parallelogram. It is a parallelopiped. Okay, this is a parallelopiped, and of course this doesn't mean that it will be this u3 will be perpendicular to u1 and u2. No, this can be squished, not squished, I mean this can be a bit skewed. Okay, so if u1, u2 and u3 are in the same plane, then we are meaning that this u3 squishes down to the plane, right? It squishes down to the plane, and if this squishes down to the plane, then there will be no height of this parallelepiped, and therefore this 3D construction will have zero volume because there is no height at all. So the formula for volume of parallel pipe, which is of course this V is equal to determinant, and here u1, u3, u2 and u3, we will adjust the components like x component, y component and z component here. So we can do that to get the volume of this parallel pipe, but we are not trying to see the volume of u1, u2 and u3 parallel pipe. What we are really trying to see or seek is R21, R31, R41. What does the volume it make? Okay, it makes, I mean, what is the volume that it makes? R41, R21, R31, and we say they squish, right? If that squishes, okay, if that thing squishes down to a plane, then it has no height, then the volume must be 0. Okay, that's our condition. Because they are in a plane, then the volume must be 0. So 0 volume, and we're going to just put these three here. So it will be x minus x1, y minus y1, z minus z1, x2 minus x1, y2 minus y1, z2 minus z1, x3 minus x1, y3 minus y1, z3 minus z1. So if we try to expand this right now, we will get x minus x1. I can put the coefficient first, I mean the cofactor. This is the cofactor here, cofactor, and we will expand in terms of this, expand from here. Okay, so we'll get x minus x1 minus, because the cofactor sign is minus, y minus y1 plus cofactor sign is positive. So another determinant. I think I should squish it down, I mean squish it leftwards. Okay, so z minus z1 is equal to 0, and these cofactors are numbers. These cofactors are numbers. We will get like for x minus x1, we'll get this thing. Okay, so we will put it here, and as a determinant, it will be a number, just a number. And this x term has 1 degree, this y term has 1 degree, this z term has 1 degree. So this equation here actually provides us an equation. This itself is the equation for the plane that we were talking about a bit earlier. So 3 points define a plane.
Bye everyone. Thank you for watching. See you later.